Hi, this is Mr. Merrill, and we're going to take a look at a quantitative interactions problem. So I think this problem is great because it pretty much points out every single difficulty you might have with these types of interaction problems. So it's pretty dense, it'll take a while to get through, but it covers a lot of the different types of things that can come up. So we have two blocks stacked on top of each other. There's some friction in between the surfaces of the two blocks, but there's no friction on this bottom surface. The blocks are connected by a rope that goes over a pulley. You can assume everything's ideal. And then there's some pulling force, let's just say by hand, on this bottom block that goes to the right. And the question is, what is the resulting acceleration of the block? Probably should say magnitude of the acceleration. So one of the first questions we ask ourselves are, what's a logical system, and is there an acceleration constraint? So here's pretty obvious that we should deal with this with two systems, and we'll just call them 1 and 2, and we should think, does the acceleration of the two systems have to be the same in magnitude? And the answer is yes, right? There's no way these can move at different accelerations. Physically doesn't make any sense. So that's going to come in later, but we should identify that when we're first thinking about the problem. So now you need to jump in the force diagrams, and you should always start with a simpler system. Intuitively, you should get the feel that there's going to be less forces acting on the top block than the bottom block. So the forces on the top block are pretty straightforward. Now, it's very important to keep up with notation here. So I think I'd like to point out where it says FN12. There's a normal force in this top block from the surface of the bottom block. Same thing with the friction. The surface here is the bottom block. So that's why my dealers here are 2. Now, and the same thing for the tension. The dealer of this tension is the string, not the bottom block. So the next thing we do is when we move on to this next force diagram is there's going to be more forces, but before we get into those, just draw the things that you know have to be there. So obviously the gravitational force pointed down. And the next thing you should think about is, are there any force pairs from the first force diagram that I drew that should also show up here? And this is a case where there's 2. So there's a normal force, so the bottom block pushes on the top block pushes on the bottom block, that's shown here in purple, and the friction, as the top block rubs against the bottom block rubs against the top block. And they're equal and opposite, all that good stuff, and I have my force diagrams and with my force pair marks and my congruency marks. Fun stuff. What I do want to point out, though, is this Fn is tied with this force of kinetic friction. There is going to be a normal force from this bottom surface, but you have to understand that there's 2 normal forces in this problem for the bottom block. There's one from the bottom surface and one from the top. And the friction is from the top surface, right? From the in between the 2 blocks. So that friction is going to correspond to that normal force from that surface, not the normal force from the bottom frictionless surface. And that's tricky, but you need to recognize that if you want to solve the problem. So now we fill out our force diagrams a little more. We introduce those other forces. Note that these 2 tensions must be the same because of the ideal string approximation, but they are not force pairs. That's obvious from the fact that they're not even in opposite directions, and the Feeler-Dealer notation is not switched. These forces do have force pairs, so they appear on the string itself. And again, this normal force is from the bottom surface. It is not tied to this friction. And then we have our pull, which I just said was from a hand. Okay, finish it off by just drawing some axes and noting the net force on both of these blocks. Intuitively, they have to have the same acceleration. The top block's accelerating to the left as the bottom block accelerates to the right. But because the bottom block has twice the mass of the top, it needs to have twice the net force to have that same acceleration. That's something you really want to wrap your head around. Now, you might want to pause here and try to write out the components to the forces on your own before I move to the next screen. Okay, so here you can see how I've listed the components. And I think there's one thing that really tricks people, and it's a notation game. So it's saying, when I'm writing the magnitudes of, say, these tensions, or these normal forces, or these frictional forces, they appear on both systems. That's because they're either a force pair or they're a match to some ideal string approximation. So you'll see that I've given them the same name. I've dropped the feeler-dealer notation, basically. Kept any negative signs or anything like that. But I've given them the same name because I know what they have the same magnitude. Whatever number goes in there goes in the other one. And that allows me to do a lot more in terms of algebra because it reduces the number of unknowns from 2 to 1 for each pair. So renaming this is a confusing thing, but it's necessary to solve the problem. So it just says rename any force pairs, the same thing, or rename any ideal string approximations, the same thing. So instead of saying ft1s here when I'm writing out the components, just call it ft. Instead of calling it ft2s here when I'm writing out the components, just call it ft, and slap the negative sign on it because it points to the left. Okay, so now we get back to the idea of an acceleration constraint. So up at the top here I have Newton's second law for each of the two blocks, just F equals ma basically. But you have to think about the acceleration constraint, because this a is a vector, and it's not necessarily the same a is over there. They have the same magnitude of the acceleration, but they do not point in the same direction. So you have to recognize that the top block is accelerating to the left. It has the same magnitude of acceleration, but not the same direction. So how do I indicate that? I have to add this negative. I would pause the video here and make sure you understand where this negative came from. It's because this top block is accelerating to the left, and this bottom block is going to be accelerating to the right. This is one of the most forgot about things, and you will not get the problem right without understanding why that negative has to be there. Okay, so now I basically plug in my components into these two sets of equations. You could plug into here too. I didn't to save space because I know I'm not going to end up using that equation. And that happens. You might not use every single equation that you generate. That's just part of the game. But what I would do here is kind of pause the video and see if you can finish the problem on your own. What we're looking for again is the magnitude of the acceleration, because everything after this point is algebra. And as much practice as you can get that on your own, it's going to be the most beneficial. So try to get it on your own. Okay, so the first thing I do is I try to fill in some gaps. I try to reduce the number of unknowns. So I don't know Fn, but I do know the mass of the first one in G. So this comes from the top block. I rearrange Fn and just say that it's equal to the mass, the weight of the top block, and that's going to substitute in my Fn's for these two horizontal equations. Alright, so now I've reduced my number of unknowns to just 2, and I've reduced my number of equations to just 2. That's great. I know from algebra that if I have 2 unknowns and 2 equations, I can solve the problem. So, here's one of the very confusing things, and no matter how many times I say it, I still see people messing it up. If you have 2 equations and 2 unknowns, and say I want my end game is A, I can't immediately rearrange one of the problems in terms of A. It won't work. Why? Because I need to substitute in. And if I'm going to be substituting in, I'm going to be substituting in terms of ft. So I need to solve for the other unknown first. So I'm going to pick the simpler equation. So starting with the one on the left, which is the simpler equation, I simply do 2 lines of algebra to solve for ft, and then plug it into the more complicated of equation here. That makes one nasty looking equation, making sure that I include these parentheses because the whole thing is going in. And that really matters because I have this negative sign here that is going to mess me up if I forget those parentheses. So next I go ahead and distribute that negative. So that's going to go dink, dink, and I get 2 negatives here and here. And then the next thing I have to do is, okay, I want acceleration. I in fact know everything else in this equation now. A lot of people don't know what to do at this point. They forget their algebra. But what you have to do is, if you have 2 terms with the unknown trapped inside, you need to move both of those terms by themselves on one side and get everything else by itself on the other side. Now, hopefully you can see the end game of this problem. 2 mu k m1g's, these two together make minus 2 mu k m1g. I can factor out the a from both of these equations and then divide both sides by this term m2 plus m1. That gives me this nice, concise formula. And in fact, I can pause here and check for my understanding. Think about, does this make sense? Would the acceleration, what would happen if one of the masses got bigger? Well, intuitively, it would make sense that the acceleration will go down. I'm pulling with the same amount, but more mass, acceleration goes down. And this formula shows this. What would happen if the pull got bigger? Well, intuitively, the acceleration should go up. I'm pulling harder, and it does because of the pulls in the numerator. What would happen if mu k was larger? Well, there's more friction, so intuitively there should be less acceleration, and we see that, the mu k's being subtracted away in the numerator. Now, this is pretty advanced level stuff if you can reason through the equations like this, but it prevents a huge number of errors if you do those mental checks, right? I basically know I've made a mistake if I get to this step and my final equation doesn't make sense. That's why I'm such an advocate to waiting for the end to plug in numbers. So play with your calculator a little bit, and you get this for the value of acceleration. Yay. Not really too important numerically. It's getting to this step, which is really going to see if you understand the problem or not. Okay. So what I would do is, this is a great problem to work right before the exam because it's so in-depth. It has so many different parts and things you have to remember that if you can do this the night before the exam without any help, you probably have a good grasp on what's going on. So to remind you to go through the equations, and basically every time I've typed something out, that's basically me recognizing that there's a common mistake there. Okay? Alright, so hopefully that helped.